Hello student, in previous lecture we have seen Cauchy integral formula with a proof. Then we have seen some problems on a Cauchy integral formula. So that Cauchy integral formula is a very important exam point of view. So I hope you all the student read that the Cauchy integral formula. So in this lecture we will see second formula, that is Cauchy higher order derivative formula. This formula is also called as a higher order derivative formula. So we will see the theorem of a Cauchy higher order derivative formula. So what is the statement of the Cauchy higher order derivative formula? In examination there will be the question, state and prove Cauchy higher order derivative formula. Okay. So this is the statement of the Cauchy higher order derivative. What is the statement? Let f g to c be a analytic function and let closure ball with center A radius r which is containing in region G. And if gamma of t equal to a plus r e raised to power it. So here A is a center, r is a radius. T lies between 0 to 2 pi. Then prove that f n of z, that means nth derivative of f of z, equal to n factorial upon 2 pi I integral over curve gamma f of w upon w minus z to the power n plus 1 dw for mod z minus a less than r. So here z minus a less than r, which represent a circle whose center a and radius is r. So this statement is near equal to Cauchy integral formula. Only formula is different. Okay. So we will see the proof of this theorem. So what is given? So we have given f is an analytic function and a closed circle whose center A radius r which is containing region G. And gamma of t also we have given a plus r e raised to power it where t lies between 0 to 2 pi. Okay. So therefore by using the Cauchy integral formula, so by using the Cauchy integral formula, f of z equal to 1 upon 2 pi I integral over gamma f of w upon w minus a dw for z minus a less than r. Let us we consider equation number 1. So to prove this Cauchy higher order derivative formula, we will use the concept of the Cauchy integral formula. Okay. So this is the statement of the Cauchy integral formula. Okay. So theory part of the Cauchy integral formula and higher order derivative formula both are the equals. So therefore by using the concept of the Cauchy integral formula, we will prove this theorem. Okay. So to prove this theorem, let us we define a function, that is phi of wz equal to 1 upon 2 pi I f of w upon w minus z. So here the w is the point which is lies on a curve gamma of t. That means we can say that the circumference of the circle mod z minus e equal to r, and z which is lies inside the circle, that means we can say that mod z minus a less than r. Okay. So here w is a point which is lies on a curve gamma, and z which is a point which is lying in a inside the curve gamma, and therefore we can say that w is not equal to z. So w never not equal to z for any w and z. Okay. So which therefore we can say that the denominator w minus z is not equal to z. If the w minus z is not equal, then we can say that w minus z is not equal to 0. So therefore phi of wz is well defined. So this w minus z is not equal to 0. So therefore phi of wz is well defined for all z satisfying mod z minus a less than r. Okay. So here also we have given function f is a analytic function which is a given function. So we know that by using the definition of the analytic function, if the function is analytic, that means we can say that that function must be a differentiable as well as the continuous. So therefore we can say that the given function f is analytic, so therefore f is a differentiable and which is also a continuous function. Okay, so f is a differential and continuous function. Then we can say that from this definition, the phi of wz is also a continuous function and differentiable function. So here phi of wz is a continuous function. Now again we will define another function, that is g of z. So integral over gamma phi of wz dw. So which implies g of z equal to, put the value of phi of w from this definition. So that is 1 upon 2 pi f of w upon w minus z dw. So let us consider equation number 2. Okay. Now by using the Leibniz rule, so here f of w is a continuous function, then we can say that g of z is also a continuous function. Okay. So since phi of wz is a partially differentiable with respect to z, then g dash of z is exists. So therefore by using the Leibniz rule, so here f of w is an analytic function, then we can say that f of w is a differentiable as well as continuous function, then g of z is also a continuous function. Okay, so hence there exists its partial derivative. Okay, so therefore g dash of z equal to integration over gamma del by del z 1 upon 2 pi f of w upon w minus z dw. So differentiate with respect to z partially. So here 1 upon 2 pi is a constant term, so take outside of the integral. So integral over gamma f of w, so this f of w, and del by del z, so derivative of this term 1 upon w minus z, that means minus 1 upon w minus z power 2 into derivative of w minus z, that is minus 1. So we can write in this way, the derivative of 1 upon w minus z, that is this term, and this dw is as it is. Okay, so this minus and this plus and this minus minus will get plus. So therefore g dash of z equal to 1 upon 2 pi I integral over gamma f of w upon w minus z to the power 2 dw. So let us reconsider equation number 3. Okay, now if you observe from equation number 1 and 2, so we get g dash of z equal to f dash of z, or we can say that g of z equal to f of z from equation number 1 and 2. What is equation number 1? So here equation number, from this equation number 1, and the equation number 2. Okay, g of f of z equal to g of z, equal to g of z. Okay, so where is g of z equal to f of z. So taking the derivative on both sides, we get g dash of z equal to f dash of z. Now we will put g dash of z, this value, in equation number 3. Then equation number 3 will becomes f dash of z equal to 1 upon 2 pi I integral over gamma f of w upon w minus z to the power 2 dw. Okay, so this is the first derivative of the given f of z. Okay, so again by applying the Leibniz rule, so there will exist a second partial derivative of the f of z. So therefore f double dash of z exists. So therefore f double dash of z equal to 1 upon 2 pi integral over gamma del upon del bar del z f of w upon w minus z to the power 2 dw. So take the differentiation with respect to z to this term. So 1 upon 2 pi is a common term or constant term outside of the integral over gamma. So here f of w, so we will take the common. So differentiation with respect to z must be the minus 2 upon w minus z to the power 3 into derivative of this w minus z, that is minus 1 dw. Okay, so in this way 2 into minus 1, minus 2 minus 2, so this can be written as 2, or it can be written as 2 factorial, upon 2 pi I integral over gamma f of w minus z to the power 3 dw. Okay, so in this way we will get the second derivative of the f of z. So if you apply the again Leibniz rule, for this, we will get the third derivative, that is f triple dash of z equal to 3 factorial upon 2 pi I integral over gamma f of w upon w minus z to the power 4 dw. Okay, so if you take the apply if you apply the Leibniz rule again and again up to n term, so we will get the n terms. So if you apply the continuously the Leibniz rule with respect to z up to the n terms, then we will get the n term is f to the power n of z equal to n factorial upon 2 pi I integral over gamma f of w upon w minus z to the power n plus 1 dw for z minus a less than r. So this is the final term, or this is the proof of the Cauchy higher order derivative formula. Okay, so many books there are written in another form. Okay, some books can be written in some books the formula can be written in this form, and some books the formula can be written in this form. Okay, okay, so these are the different types. Okay, the above formula can be written as fn of z0. Instead of z we can take z0. Z0 is an again point n factorial upon 2 pi integral over gamma f of z upon z minus z0 z0 to the power n plus 1 dz, where z0 is any point in a circle mod z minus a less than r. Or uh, we can write in this way: integral over gamma f of z upon z minus z0 to the power n plus 1 dz equal to 2 pi r. So multiplying this 2 pi to this term and n pi dividing time. Okay, so 2 pi upon n factorial fn of z0. Okay, so Cauchy higher order derivative formula can be written in this form. Okay, so this form is very important when you are going to solve the problems. So that time you have to use this second formula. Okay, so this second formula is easy to understand to solve the Cauchy higher order derivative formulas problems. Okay, so here we will stop. In next lecture we will see the some problems on a Cauchy higher order derivative formula. So that problems will be very important, again exam point of view. Okay, so you have to read all the step by uh, step of this um, theorem. Okay, so this is the complete proof of the Cauchy higher order derivative formula.